Welcome to Free Learning Academy. Let's simplify starvation and aging. Have you ever noticed that sometimes, even when your system is powerful and fast, a particular program seems to wait forever to get CPU time? It feels like it is stuck. Not because the system is slow, but because something unfair is happening behind the scenes. This is exactly where the concept of starvation comes into play. And it is one of the most important problems in CPU scheduling. To understand starvation, imagine a scenario where multiple processes are waiting for the CPU and the scheduler keeps choosing certain processes again and again while ignoring others. The ignored processes are ready to run, they are not blocked, they are not terminated, but they are simply not getting their turn. Over time, this delay can become extremely long, sometimes even indefinite. This situation is called starvation. It is not a system crash and it is not a deadlock, but it is still a serious issue because some processes are effectively being denied service. Let's take a simple example. Suppose you are at a ticket counter and there are two queues. One queue is for VIP customers and the other is for regular customers. If the counter keeps serving VIP customers continuously and never switches to the regular queue, then the regular customers will keep waiting forever. Even though the system is working, those customers are experiencing starvation. In operating systems, this happens commonly in priority scheduling algorithms where processes with higher priority are always selected first. Now, think about how this connects to what we studied earlier about scheduling algorithms. In priority scheduling, each process is assigned a priority value, and the CPU is given to the process with the highest priority. This sounds efficient, but it creates a problem. If new high priority processes keep arriving, low priority processes may never get a chance to execute. They remain in the ready queue, waiting endlessly. This is the classic case of starvation. This problem becomes even more visible in real world systems. Imagine a system handling both system level tasks and user applications. System tasks are often given higher priority because they are critical. But if they keep coming continuously, user applications may suffer. For example, a background application like a file compression tool may take a very long time to complete. Not because it needs more CPU time, but because it is not being scheduled fairly. So the question is, how do operating systems solve this problem? This is where the concept of aging comes in. Aging is a technique used to gradually increase the priority of processes that have been waiting for a long time. In simple terms, the longer a process waits, the more important it becomes. Let's go back to the ticket counter example. Imagine that the system starts increasing the priority of regular customers the longer they wait. After some time, even if VIP customers are still arriving, the regular customers who have been waiting for a long time will be served first. This ensures fairness. No one waits forever. In operating systems, aging works in a similar way. Suppose a process starts with a low priority. As it stays in the ready queue without getting CPU time, its priority slowly increases. Eventually, it becomes high enough to compete with other processes and get scheduled. This prevents starvation because every process is guaranteed to move forward over time. Let's take a practical example to understand this better. Assume we have three processes, P1 with high priority, P2 with medium priority, and P3 with low priority. If new high priority processes keep arriving, P3 may never get CPU time. But with aging, after waiting for a certain duration, P3's priority increases from low to medium and then from medium to high. At some point, it will be treated equally or even better than newly arrived processes, ensuring it finally gets executed. Another important point to understand is that starvation is not always obvious. Unlike a deadlock where processes are completely stuck, starvation can be subtle. The system keeps running, tasks are being completed, but some processes are silently suffering. This is why operating system designers pay special attention to fairness while designing scheduling algorithms. This also connects to the broader idea of scheduling criteria that we studied earlier, like waiting time and response time. Starvation directly affects waiting time. A process experiencing starvation will have an extremely high waiting time, which is undesirable. Aging helps balance this by ensuring that waiting time does not grow indefinitely. It is also worth noting that not all scheduling algorithms suffer equally from starvation. For example, round robin scheduling reduces the chances of starvation because every process gets a fixed time slice. Since the CPU cycles through all processes, no process is ignored indefinitely. However, in priority based systems or shortest job first algorithms, starvation can be more prominent if not handled properly. Let's consider another real life analogy. Think of a classroom where the teacher keeps asking questions only to the top students. The weaker students never get a chance to answer. Over time, they become completely disengaged. Now imagine the teacher starts giving more chances to students who have not answered for a while. That is similar to aging. It ensures participation from everyone and maintains balance. In modern operating systems, starvation is carefully managed using a combination of techniques. Aging is one of the most common solutions, but schedulers also use hybrid approaches, combining multiple strategies to ensure both efficiency and fairness. The goal is not just to execute processes quickly, but to make sure that no process is ignored. So, when we look at CPU scheduling as a whole, it is not just about choosing the fastest or shortest process. It is also about making fair decisions. Starvation reminds us that a system can be efficient but still unfair, and aging ensures that fairness is restored over time. As we move forward to more advanced scheduling techniques like multi level queues and feedback queues, you will notice that these concepts are built with starvation prevention in mind. They try to balance priority, responsiveness, and fairness all at once. Understanding starvation in aging now gives you a strong foundation to appreciate those advanced designs. That is it for this video. See you in the next one.